So we stopped here, right? Charging current contribution.
Yes, we stopped here.
Okay. So let us continue from here.
Okay.
Okay, what is the role of a unit transformer in a high resistance neutral grounding system? That we have to understand. See, when we ground a generator with a high resistance neutral grounding, the unit transformer plays a very important role.
Hmm.
What is it? See, we have relays to sense the fault and trip the breaker, right? But
Yes.
these relays get input from current transformer. The relay, whether it is your normal relay or normal relay, let's say if you have a 1000 amps, if you have 1000 bar 5 amps CT or 1000 bar 1 amp CT, the fault current, phase fault current may be in the range of kiloamps. Okay, so the relay pickup will maybe 1.5 time or 1.2, 1.3, whatever it is. If it is earth fault current, the relays pickup may be, let's say, 10%. Okay, so 1000 amps CT relay pickup may be 100 amps for earth fault current minimum.
Yeah.
So when we use a HRNG system, if the fault current is 10 amps or 5 amps, our normal relays cannot sense and trip it. Okay, so,
Right.
so we cannot, protection becomes very complicated. And
Yeah.
also, see what is relay coordination. Suppose there is a fault in an outgoing feeder, and let's say there is a fault in an outgoing motor feeder. If that outgoing feeder fails to trip, my incomer has to trip, right?
Yes.
So the CT in the incomer also will see the fault. The CT in the outgoing feeder also will see the fault.
Yes.
Only difference is actually the time grading will be done. So all
Right.
these relay coordination, basically what we do is the relay will have to see the fault current. When the fault current is very less, let's say if the fault current is 2 amps or 3 amps, imagine what will be the, if imagine the fault, how you can do the coordination. The coordination also is very tough. Okay,
Yes.
so that is why unit transformer is very important. If you don't use a unit transformer, you cannot achieve relay coordination, you can't achieve this current based relay sensitivity, selectivity, all those things. Okay, now,
So, sir, unit transformer is the transformer which is after the generator, before the transmission line.
yes, before, after that
Okay.
generator, you saw generator circuit breaker. After
Yes, sir.
generator
After that.
breaker, there was a transformer, right? 11 bar
Right.
220 kV or 20 kV bar 220 kV, whatever, that is called unit
Yes.
transformer. Now that
Okay.
transformer, if it is not there, then protection is almost, I'll tell you, impossible. Okay,
Hmm.
so that is one reason that transformer is required. Second reason transformer is required, I told you previously, that there is a delta winding, and the delta winding will prevent charging current from the system getting into the generator. See, there's no unit transformer. What will happen is charging current will become very high. And if charging current becomes very high, for a fault inside the winding, your generator winding will get burnt out. Okay, that is why unit transformer second one main function is it will stop the charging current from the system entering into the generator. Okay, and that it does because there is a delta winding.
Right.
So as I told you, in a high resistance neutral grounding, the limit is 10 amps. The 10 amps limit you cannot reach if you don't have a unit transformer. Okay. And one more thing is system fault current. Our system, no power system,
Yes.
that has a very big fault level, right? What
Yes.
is the value of power system fault current? Any idea?
At distribution level, it was 65 kA.
Okay, let's say 65K or 25K or 50K, whatever. Now, if there's no unit transformer, imagine that much fault getting into the generator.
Yes.
It would be very dangerous, right? So
Hmm.
unit transformer in a way is also doing the purpose of isolating your external and the generator.
Okay.
There's one more very important. See, when we parallel generators, there is a circulating current will take place
Hmm.
because all generator winding, you see there is some small amount of harmonic voltage, third harmonic voltage. But when you have a unit transformer, the circulating current will not be there. It will prevent that circulating current. So unit transformer has lot of advantages. Okay, but everything comes with the money. If you want unit transformer, you have to pay a lot of money, and also it occupies a huge space. Yes, but we have to spend on it. We have to have it. Okay. Any doubt till here?
For generator, for in generator for this earth fault sensing, then what do we do, sir? We go for core balance CT, or how we sense that 10 amps
Yes,
coming back to the
I
generator?
will. I will. In one of the slide, I will explain that to you.
Okay. Okay.
Basically, we use voltage-based relays. I will.
Okay.
I will explain about that in one of the slides. Okay. Then see fault current beyond the transformer. Any fault at the secondary of the unit transformer, let's say at the 220 kV side, it will not be low. Okay, that will be very high, and the magnitude of that will depend on the transmission line and other things. And in the morning, I told you I will explain you about the sequence network of high resistance neutral grounding. Okay, you see, any network we can make positive, negative, and zero sequence network. Okay, so the zero sequence. So if you want to study single line to ground fault, you have to add positive, negative, and zero sequence, all three in series. And zero sequence network is very important whenever there is an earth fault involved. See, neutral resistor is present from the neutral point to the earth. I will show you now in one of the circuit how neutral resistor is in parallel with the stray capacitance. See, when you saw the actual circuit, you saw stray capacitance was from phase to ground and neutral
Yes.
resistance was from neutral to ground. Okay.
Yes.
So from that, it is not, you are not able to make out that they are in parallel.
Hmm.
But when you see the sequence network, you will see that they are in parallel.
Hmm.
As okay. Now, what is the value of current that flows through the NGR? From the sequence network, we can make out that the current flowing through NGR is voltage divided by 3 times Rn. That I will explain you when I by putting the network now. You this one let us you know now you are able to see this is a NGR
Yes.
connected in the neutral. Now this one is like a single line diagram. Okay.
Yeah.
Now you see here uh, you can see here the reactance. This is the generator XG double dash, right?
Yes.
Then you have the cable reactance. Then you have your transformer and system
Transformer.
reactance. See, here one thing is missing. Can you tell me what is missing here?
Um, the resistance.
Yes, you are correct. I have left the resistance there. Actually, the resistance should have been considered there. So resistance should come here, right?
Yes, correct.
It should come here. Now this one, what you are seeing is what? Positive, negative, or zero sequence?
Positive.
Positive sequence network. Now, positive and zero sequence network are almost identical. Only difference in negative sequence, you will not have voltage source. Okay.
So whatever we find in the nameplate, sir, is positive and negative, right? Both
What
are
you
same.
find in the nameplate is positive sequence,
Okay.
and positive and negative are always same.
Okay.
And what you find zero sequence, sometimes you get in the test data also.
Test report, right?
Test report. Now see here, this is the positive network. Okay. I am connecting it in series with a negative sequence network, and then I'm connecting it in series with a zero sequence network. Okay.
This is for the generator alone or the complete system, sir.
When I say x1 here is sum of all these.
Okay.
So positive sequence network of the network. When I say network, see if the fault is here, no, see this place.
Yes.
You have to find the Thevenin equivalent impedance at this location. You know the Thevenin's theorem, no, circuit theory.
Yes, sir. I studied in engineering.
Yes,
After that,
yes,
did not.
yes. Same thing. You have to actually go back and refer to that.
Yeah, yeah.
And
Okay.
from that, actually, at this point, you have to find the Thevenin's equivalent impedance, and that is
Okay.
this x1.
Okay.
Similarly, here, if I replace everything by negative sequence, I will get x2. Normally,
Okay.
x1, x2 are equal. And the difference in this positive network and negative network is, in the negative network, no, you don't have voltage source. And in the zero sequence network also, there is no voltage source. The zero sequence impedance is not equal to positive or negative. It will be higher, and that you have to get from the manufacturer data sheet or test report. Okay. Now x1, x2, x0 you got from the network. To this
Yes.
here, you have to add this 3Rn also.
Okay.
So 3Rn, why 3 times Rn is because, see, when something is present in the neutral, IA, IB, IC, all three current will flow through it, right?
Yes, correct.
That is the reason when you convert it to a sequence network, it will become 3Rn.
Can you repeat, sir, that one point, please?
See, IA current, IB current, IC, all three phase current are
Okay.
flowing through the resistor. Okay.
Okay. Okay.
And when you convert that phase network to zero, this, see, phase network is basically ABC network,
Hmm.
and sequence network is a 0, 1, 2 network. So basically you have matrix. You have studied this matrix, no? Z matrix, Y matrix.
Yes.
So when you convert Z matrix having ZA, ZB, ZC to a Z matrix of Z0, Z1, Z2, this Rn value in the phase will become 3Rn.
Okay. Okay.
Okay. So basically the matrix transformation, but that is about maths. But in reality, why it is happening is because normally neutral, all three current will flow through the neutral. IA, IB,
Right.
IC. Okay. And
Right.
some of them is zero. So that is why it is 3Rn. Now XC is in parallel. See this XC, no, will come in
Hmm.
parallel here. See what is XC? XC is basically a current which will flow to the, uh, it is like all three phase current is flowing, charging current, that is a zero sequence current. Okay. So that is why
Yes, sir.
it is coming here. Okay. Now, after you draw all these together, then you have to add the fault resistance here. Then you can
Okay.
compute take this as 1 per unit, do on per unit calculation, you will get the fault current. Okay.
Okay.
So actually you go through this book, Stevenson Power System Analysis
Okay. Power system analysis.
by Stevenson.
Okay. Okay.
It will be clear. Okay. Because symmetrical component is a very big topic.
Okay.
It will take almost in the engineering itself, they cover it for weeks together.
Right.
And now since we are out of college, it will take months together for us to learn.
Yes, sir.
Okay. So, but basically what I want you to understand is the 3RN and XC are in the zero sequence network, and these two, if you neglect X0, these two are is almost parallel.
Yeah.
Okay, and fault current you
Yes.
can say is almost equal to the resistive component is V divided by 3RN, or V phase divided by 3RN, we can say. Okay, that is why I'm telling here V by 3RN.
Okay.
So now this fault current, you remember in the first slide, one of the slide I told about damage curve,
Yes.
and in the damage curve I also told about this one. What is it?
Time for.
Time constant. And I told you we cannot change the time.
Yes.
Time constant is one thing. Another is the time. I told you we can't change the time.
Right.
See, normally when a fault take place, breaker will open. But in a generator, see, if a fault take place, the amount of time for which my fault flows, I can control
Hmm.
by opening the breaker, right? But whereas in this high resistance neutral grounding system, it is not like that. I will explain you why. So this is a very important concept. Please understand. See, fault has taken place in this winding. Okay. Now
Yes.
fault has two component. One is the resistive component. One is the capacitive component. Okay. Now
Yes.
winding fault is a very big fault. There is some trip, no, class A, class B, class C trip.
Yeah.
Since it is a very big fault, what they will do is they will trip the generator circuit breaker. Okay.
Yes.
After tripping the generator circuit breaker, you are out of the system. But turbine also has to be tripped immediately. Turbine coupled to the alternator also is tripped immediately. But the field breaker, no, I cannot trip immediately, because if I trip this field breaker immediately, what will happen? Field is basically a coil, right?
Yes.
What will happen if I trip the field breaker immediately? Any idea?
We will have voltage induced.
Okay. So you have heard about this L di by dt?
Yes. So amount of EMF produced is uh, depending on L and rate of change of current.
Yes, rate of change of current. So the current magnitude changes suddenly, right?
Yeah.
So when current magnitude changes suddenly, there is a huge voltage will develop. So if I interrupt my field current suddenly, no, if I open the field circuit breaker, the huge voltage will get induced here. That may
The
even,
field winding, is it?
yeah, in the field winding.
Okay.
That may damage the insulation.
Okay.
That is the reason what they will do is, first actually they will they will close this breaker.
Okay.
They will close this breaker. And when they close this breaker, and then they will open the breaker. When they close this breaker, what will happen? Immediately you have to open this breaker also. The current will start discharging inside like this. See, field current was constant. Okay. I will close this breaker and open this breaker. My field will discharge on its own. So you see, current is not made zero in very short duration. Current is slowly made to fall down. So
This field winding is generally we give DC to this one, sir.
pardon?
Field winding, do we generally give DC voltage to this one?
The field winding is DC only,
Okay.
and this current is made to decay, and the
Okay.
time taken for the decay is proportional to the open circuit time constant TDO double dash.
Okay.
So this TDO double dash, we have two constant, open circuit time constant, short circuit time constant.
Mm.
The open circuit time constant is the one which tells about how the field decays. Okay, so that from that you will get this. So you see, you understand now why I told about this. Now you come to, okay, I told you about field.
Yeah.
See, the next thing is the turbine is running, right?
Yes.
Turbine cannot stop immediately. It is a rotating mass. Turbine, generator, and exciter, all three are in the same shaft. And power plant, the shaft is having a huge mass. So as soon as you stop, it will not stop.
Yes.
Means as soon as you see, you have stopped giving steam to the turbine, but it will not immediately stop.
Yes.
So it rotates for some time. So here two phenomena are taking place. One is the turbine shaft is rotating for some time. Number one. Number two, your field winding excitation is also slowly ramping down. So, which means until then, the generator is generating power.
Yes.
Maybe not huge, but small amount of power is generating, and slowly it is falling down to zero, right? Now, this current cannot go out, and the voltage will be there, but current will not go out. Breaker is open. So that current will drive the fault. Okay, understood?
Yes, sir.
So you see here, my fault took place here. This is my winding fault current. Okay, you can see my in the winding, the fault current is growing like this, and actually, ideally speaking, immediately it should have become zero, right? As soon as
Yes.
I
Yes.
trip, but it will not become zero because my shaft is rotating and my field is slowly decaying. So you can see here the current is there.
Mm.
Okay,
Yeah.
so this current now, if you integrate this will give you the arc energy. So that I see why in a motor, as soon as there's an internal fault, if I trip, maybe in a 1 second it will stop. Whereas as the generator become bigger, the TDO dash constant is more, and the for maybe 10 or 15 seconds this will be there internally. So imagine the amount of energy,
Yeah.
and that energy can really damage your stampings. Okay, so that is the reason we go for high resistance neutral grounding in a power plant. We want, at least we want to reduce the current. We cannot reduce the time. At least let us reduce the current. Okay. That is clear, no?
Yes, sir. Clear.
Okay. Now fault inside a winding of a generator will not stop when generator breaker trips. Generator side contribution will stay until field current decay. The time period depends on the time constant TDO dash. Line breaker and field breaker are tripped after false is sensed by relay. Field current cannot be interrupted to zero suddenly. Why? Because large di by dt will create a huge over voltage in the field current. So the field bypass breaker is closed. Okay, and when large fault takes place, turbine is also tripped. And because there is a common rotor, it has a huge inertia of the rotating mass. So rotation along with the remaining flux drives the fault current. From
Yep.
where do you get the open circuit time constant of the machine?
We'll get it from OEM.
Yeah, you are correct. We get it from the generator vendor. The typical value of this TDO dash is how much? 5 MVA generator is 1 second. And you can see for a 50 MVA generator, it is 10 seconds. Okay.
10 seconds.
Yeah. So imagine for a 600 megawatt generator, it will, it will be very huge. Large generator, large time constant. Okay.
Okay, sir. Clear.
So high resistance, neutral grounding, and unit transformer are very important for large generator because we have prevent damage to the stator. Any doubt till here?
No, sir.
Have you come across unit transformer?
No, sir. In one of the plant we had this generator. 5 generators are there, and all 5 generators in series we have unit ratio transformers, like to reduce the fault current. But I have not come across this unit transformer in generating station.
What was that generator voltage rating?
It was 11 kV, sir. 5 numbers of 2.5 MVA 11 kV generators.
Okay, 5 number of 2.5 MVA 11 kV.
Yes, all 5 generators had a unit ratio transformer in series.
Okay, 11 bar 11.
11 bar 11, yes.
And that 11 kV generator, what was the type of earthing you used?
It was we had a neutral resistance there, but I'm not sure if it was high or low resistance.
If you have a I think maybe you are using low resistance neutral grounding.
Yes,
and
I did not know this that time, so I did not check that.
And the transformer, what you are telling, no unit ratio transformer.
Yes, sir.
That is also like a isolation transformer.
That is also ISO. Yes, sir.
Because of the transformer, your third harmonic circulating currents are not there.
Okay.
And because of that unit transformer, your system fault current will not enter your generator.
Right.
So though there is no high resistance grounding there, and third advantage is actually when you do relay coordination, I think the transformer primary may be delta and secondary may be star grounded. Do you remember transformer
will have to I will have to check that, sir. I will maybe by till tomorrow morning I can get that.
Most probably the secondary it will be star grounded. And primary will be delta. And this is the reason. Prevent the circulating current, prevent fault current entering from the secondary to primary, and what is the third thing? And for relay coordination, it will help.
Sir,
Okay.
one thing is for North America, I told in the morning that we are using this high resistance ground in a transformer.
Yeah.
So there, what happens is the earth fault is reduced to 5 amps,
Okay.
and the system will remain on during the first fault. And after that, what they do is they look for, and there will be an alarm that there is a first ground fault. So
Yeah.
they will trace the ground fault, and that particular feeder they will isolate, and the plant will still be running.
Yeah.
For this, they have one panel where this is called as a ground fault monitoring panel,
Okay.
and that panel will keep on checking if there is any current through the uh, high resistance,
Yeah.
and if there is a current, it will give an alarm.
Yes. You're perfectly correct. Even what I have gone through also is the same. When they have a fault, they don't shut down the system, and
Yes.
the they will either do a changeover or something, trace the fault, give alarm. Yes, this is one of the
So,
practice.
so in this case, what happens is for all the feeders that are coming from the transformer, they are installing one CBCT sir,
Okay.
because the ground fault is not, they cannot sense this ground fault at, like what you said, they cannot sense this ground fault in that CT. So they go with the CBCT to understand if there is a ground fault in that individual feeders.
Okay. CBCT you can put, you can stick to few amps and you can put that you
Yeah.
can. But if your fault take place somewhere far away in the feeder,
Uh,
maybe you have to go for voltage based relays also.
okay.
Now, how do we design NGR and NGT? That let us understand that one. See, finally, as a plant engineer, you want to buy NGR, you want to purchase NGT. So, if you want to purchase that, you have to make a data sheet and specification, right?
Yes.
Now, to make that data sheet and specification, what you have to do is you have to know how to do the calculation first, right? Later on, I can write metal enclosure, ingress protection, that this. But first thing is I have to know the value of NGR, how many ohms, value of
Yes.
NGT, how many kVA. First I have to know that, right?
Yes.
So that is the objective. For that, what is the data first you need to get generator data. Have you seen big generator data sheets?
I have seen for the plant generators,
Okay.
uh,
What rating?
maximum 2
What rating?
1 MVA to 2 MVA. Sir.
Okay. So that generator data sheet also is very big. But that generator, I don't think they'll give you capacitance, winding capacitance.
Yes, sir, they don't give.
But if you go for this megawatt scale, 50, 100 megawatt, there they will give the capacitance, winding capacitance.
Uh,
So first is you have to get this generator voltage and winding capacitance. Okay. After you get that, so as I told you in the morning, if there is a generator circuit breaker, please check whether there is surge capacitance. If surge capacitance is there, that also you have to take into account, otherwise no. Isolated phase bus duct and transformer winding capacitance you can neglect. Then next is you determine XC. After getting XC, you determine RN. Okay, that how exactly I will show you the calculation. You can do it. Do you have scientific calculator with you?
I have Excel now.
Okay, that we will do tomorrow, the calculation. Okay.
Okay.
Now, you have to fix NGT secondary voltage. See, neutral grounding transformer, what should be the voltage rating of the primary and secondary? Can you tell me what should be the voltage rating?
Primary can be generator voltage by root 3.
Primary can be how much?
Generator voltage divided by root 3.
Okay.
And secondary can be based on our resistance.
Okay, you are correct.
Whatever
Primary can be the generator voltage divided by root 3. Okay. But what people do is they will multiply by 1.3
yes.
because to take care of this saturation and so on. Okay, and why primary should be proportional to phase voltage? Why not line to line voltage?
Because it is always connected to phase and neutral only.
You're correct. Actually, whenever a fault takes place, it is single line to ground fault, phase to neutral. So it is phase. When there is a fault, one of the phase falls on the earth. So your NGR, one side is connected to phase, other side to the neutral. So it is phase to neutral voltage. Okay. So what we do is we take phase to neutral voltage, multiply by 1.3 to prevent saturation or whatever it is.
Okay.
Okay. And the secondary voltage, we will take it as 220 volt.
Okay.
And some people may take 300, some people may take 400. Different practice exists.
Okay.
If you have come across some other voltage, you can let me know.
Okay.
Then the resistor voltage rating will be same as the NGT secondary voltage. So I will choose 220 volts. I will take both 220. Okay. Next is I have to determine the turns ratio of the neutral grounding transformer. What will be the turns ratio?
Primary by secondary voltage.
Yeah, primary, let's say, is 11 kV by root 3 into 1.3. Okay.
Okay.
11 by root 3, maybe 6.36 volts into 1.3 is how much? So it will come to
8.25.
8 kV. How much?
8.25.
8.25 kV. So my 8.25 kV divided by 220 volts is how much?
37 is the turns ratio.
How much?
37.
37. So my turns ratio, some typical I'm just telling.
Okay.
Need a NGT which is 37 turns. Why
Turns.
turns ratio is so important? Can you tell me? Morning I had explained it.
Because the fault current, we have to make sure that the fault current is restricted. The ground fault current is restricted to 10 amps. So based on this turns ratio, we will size the resistance value.
R is it the resistance we have no R divided by N square. Whenever
Yes.
a resistor is connected in the transformer at secondary, its total value in the primary will be R by N square.
R by N square. Okay. Okay.
Okay, so the amount of resistance that is seen by the neutral. See, for neutral, it is not seeing transformer and resistor as separate. For it, it is one unit, right?
Yeah.
The neutral will see how much resistance. The resistance seen by the neutral is R by N square, where R is the resistor value
In a
of
second.
the NGR and N square is the turns ratio of the NGT. Okay.
So R is in secondary and N square is the turns ratio.
Yes,
right?
yes, correct, correct.
Okay. Okay.
So now you understood the advantage of using transformer.
Yes.
If I use a 1 ohms resistor, okay, 1 ohms You multiply by 33. What is the turns ratio you got?
37.
So 37 square is how much?
1408.
How much?
1408.
1408. So if I have a 1 ohm resistor, no, in the transformer
Yeah.
secondary, the resistance seen by the neutral is 1408 ohms.
Yes.
Okay. So you see the advantage of using NGT. Okay. So now next I have to calculate. Okay, Rn value. How do I get? I told you, no. I will explain to you. Rn is related to Xc.
Yeah.
Actually, what happens is first I will get Xc, and from Xc I will get Rn, right? That Rn what I get from Xc is the Rn in the primary. Okay.
Right.
After getting turns ratio, I have to determine Rn in the secondary side.
Right.
Okay. After getting the Rn, the next thing is I have to determine what is the resistive component of the earth fault current. Okay. That is, after I get resistive component of the earth fault current, whether primary or secondary. Primary current I will multiply with primary voltage. Secondary current you multiply with secondary voltage. Finally, you will get the kVA rating of the transformer, and also I will come to know what is the ohmic value of the resistor. Okay, this will be clear when we do calculation.
Okay.
And one more thing is, you remember the neutral grounding transformer is run for, we operate it for how long? Any idea?
Only during the fault, and till that fault is completely subsided.
Yes. But the fault may be there for 10-15 seconds.
Yes, sir.
People have practice of using it for 30 seconds, 1 minute, 3 minute, like that. They have developed a lot of practices. So basically, it's a short time rating.
Yeah,
So
shocking.
if I calculate, let's say 20 kVA as the NGT rating, don't compare it with the 20 kVA power transformer, okay, or distribution transformer. 28 kVA transformer for NGT is much smaller than the distribution transformer, because this is a
Right,
short
right.
time rated transformer.
Yeah.
So basically what they will do, if I ask 20 kVA transformer, they will divide 20 by 2.5, okay, and they may use a 8 kVA transformer, or they may divide 20 by 4, use a 5 kVA transformer. But we should not bother what is the continuous rating, okay. So
Okay. Okay.
let us only bother about the short time rating.
Short time.
Manufacturer is guaranteeing you that it will carry 20 kVA for 30 seconds, means he is doing the testing.
Mm.
So let us not, because some people have practice of specifying continuous rating also,
Okay.
which I think is not correct. Okay.
Right.
For having a fair idea, fine, but not specifying. As I told you, continuous rating you determine, but don't stick into it very hard. And finally, we need the ohmic value of the NGR, right? Because
Yes.
when you go for testing, I want to know what is the resistor he has used, how many ohms. 220-volt resistor he has used. I want to know what is the ohmic value.
Ohmic value.
I may ask him, please measure and show me the RDC, right? So
Yes.
ohmic value, we have to get it. How we get it? Ohmic value, as I told you, you know the Rn in the primary, so you know the Rn in the secondary.
Secondary. Yes.
Rn primary and secondary are related by that square of turns ratio. And NGR time rating, as I told you, find out what is the practice by the owner, plant owner, okay, and follow it. That's all. If plant owner say I want 30 minutes, give 30 minutes. Okay. Then finally you have to prepare the specification of NGR and NGT. Now coming
That is similar to what we did for low voltage, low resistance grounding, right, sir? Enclosure
yes,
and everything almost.
similar to that, but here actually the spec is almost same as that because
Okay.
the resistor is same, almost same resistor is used here also.
Okay.
There is no difference. Okay. Now coming to this neutral grounding transformer, see you have to specify the neutral grounding transformer also. As I told, neutral grounding transformer carries fault for a very short duration. And see, you have two type of transformer, no oil and dry type. And most of this transformer used along with NGR is a dry type only, not oil type. Oil type has more overload rating than dry type. Okay. But we are using dry type transformer, and dry type transformer calculating the overload rating is little difficult. In a oil type, okay, they are giving up to 4.7 time it can carry overload for 1 minute. Okay, up to 2.6 time it can carry for 10 minutes. Up to 1.9 times it can carry the overload for 30 minutes. Okay, and the overloading of the transformer depends on ambient temperature, hotspot temperature, then winding oil temperature, rise limit, insulation material, loss of life, etc. But if it is a dry type transformer, there is no oil, but still you have winding temperature rise, you have the insulation material, all those things are there. So this overloading factor of dry type transformer, are you aware?
No, no, sir. I'll
Okay.
have to study.
Just stuck. If you get some value, you please share.
Okay.
Okay. So that is we are actually that is the reason I'm telling. Let us not specify the continuous rating.
Rating. Okay.
Let us specify the short time rating of the transformer, and let us specify the time rating also, and let us verify that one when we do the test. See, actually, practically speaking, your NGR, NGT will not be loaded for more than few seconds because of the TDO dash. What is TDO
Yeah.
dash? Open circuit
The
time constant.
time constant.
What is the typical value of TDO dash?
Around 10 seconds.
10 seconds. But some people are, so it is basically a short time. See, this entire process is a short duration process, right?
Yes, correct, correct.
So why do I need to specify continuous rating? Not required, right?
Not required. Yes.
So if it is for 10 seconds, let me specify 1 minute. Let me just say, give me a NGR, sorry, give me a NGT of 20 kVA for 1 minute, right?
Correct, correct.
And when I go to the test, let me tell that you load it 20 kVA for 1 minute. I want to check. That's all. Enough, right? So why should I specify 30 minute, or why should I say continuous rating of this transformer is 5 kVA? Is it required?
Not really.
But some people have the practice, and okay, just, and it is actually not practically possible to determine the short time rating by us. It is the vendor who can do it. Okay. So as I told you, utilities are giving 30-minute rating also. It is not required. See, 30 minutes is how many seconds? 60 into 3, 1800, right?
Yes, yes.
Let's say my TDO dash and all multiplying factor and all come to 18 seconds. So 1800 is how much? 100 times, right?
Yes, it's
Why should I give 100 times rated? Yeah, but people have developed the practice. Maybe olden day they had a different practice and it might have continued as it is. Okay. As I told, dry type transformer overloading capability is much less than oil type. Now coming to this basic insulation level, as I told, NGT is connected in the neutral. So the voltage, see, it is close to the ground voltage, right? When there is no fault, what will be the voltage?
it will be very less based on
It
the
will be almost zero.
almost zero.
Now during fault, what is the voltage?
It will rise to the line to neutral voltage.
Yes, it is line to neutral voltage. Now, see, voltage cannot go beyond line to neutral, no?
Yes, sir.
So if we go for the line to neutral voltage, according to me, it is enough. Okay. And to take care of saturation, some people are multiplying it by 1.3. That is also fine.
Right.
But some people have practice of using line to line voltage. One reason what I feel maybe because they want to have a standardized transformer. Getting 11 kV transformer. See 11 kV, what should be the rating of the NGT primary?
It is 6.35 is by
11 by root 3 into 1.3 is how much?
8.2 kV.
8.23. Actually, when I say I want 8.23 bar 220 volt transformer, for vendor also getting that 8.23 is a headache. So he will give 11
Yes.
kV bar 220 volt and he will tell 8.23.
And it is not going to increase too much of cost
Yeah.
also.
So maybe that is one reason some people are directly specifying line to line voltage.
Right.
Okay. So, as I told you, if line to neutral is taken care, that is sufficient. And to prevent saturation, we have to multiply by 1.3. See, when I say saturation during a fault, when the current changes suddenly, that can also lead to saturation of the magnetic core. But I will not go more deep into this saturation. Now, this construction of NGR, you are there in the low resistance neutral grounding, right?
Yes, sir.
So, same thing I'm revising again. NGR is made of basically steel strips and wound conductor or punched steel plate or grid, right? So basically it can be either a plate or a winding. And the resistance has to have low temperature coefficient. You know very well why temperature coefficient has to be low, because if the temperature coefficient is less, what will happen? The resistance
The
value
heat.
will not change much, right?
Yeah. Yes, correct.
And what should be the material of NGR? Common steel can I use?
Common
Stainless,
steel, yes.
normal stainless steel, can I use it as NGR?
No, sir. We have to have an alloy which is having a negative temperature.
Low temperature coefficient.
Yeah.
And I use steel instead of copper because steel resistance is high.
Yes, compared to copper.
And you know the concept of you know the concept of positive and negative temperature coefficient, right?
Yes.
Yeah, positive. What is positive temperature coefficient? Resistance will increase, right, with temperature.
Increase with the temperature.
And negative temperature coefficient, resistance
It
drop.
is the opposite.
Negative
Yes.
temperature coefficient where we have in transistors. Yeah. So now, what are the different alloys? AISI 304, AISI 310, AISI 340, nickel chromium steel. These are just few of them. When you are buying NGR, you can ask the vendor. Okay, vendor will tell you what material is using, but sometimes it is proprietary, so you cannot ask.
Yeah.
Stainless steel 316 is not recommended. The temperature coefficient will be very high. So what is the new resistance? You have to find out what is the change in temperature, multiply by the positive temperature coefficient, multiply by the resistance,
Plus
and then you add it with the original resistance. In other word, if my new temperature is 330, my ambient is 30, rise in temperature is 300 degrees Celsius. Okay. Then if I have to multiply it by, let's say, temperature coefficient, and I have to
into the
multiply
resistance.
it by the resistance and then add it with the original. So I'm getting 127 ohm. This one I just took example of stainless steel 0.0009 positive temperature coefficient. Normally we don't take stainless steel because the PTC is very high. IEEE 32 is recommending PTC value to be below 0.000263. Okay. So when you go for any FAT or any test, you can actually verify this temperature rise also. The specification, okay. So what we do, we stop here today. Okay.